I have a random question before we start. That's okay.
Oh,
Go for it.
we're going live now, but
Doesn't bother me if it doesn't bother you.
yeah.
It's good. There was this work done on deep networks trying to estimate 3D poses of objects from monocular
Yeah.
images, and I forget the name of that paper. Could you remind me if you remember that?
There's a
I think
lot
from
of
CMU, pretty recent.
uh,
That they've been having known objects in the scene, so they have some supervised learning done in the background.
I can send you some pointers, but there's a massive literature now on estimating pose of known objects from deep perception. There's even a benchmarks competition that can show you this year's leaderboard and stuff like this. A few people are working on post CNN for a project as canonical.
That's the one. I think that was the one I was thinking about.
But I think that's NVIDIA, not CMU.
Okay, so I was wrong twice, but thank you.
Sure.
Yeah, because I was thinking that could be a cool addition to our project. Anyway, thank you.
Yeah, that's great.
Matt also shared the nerfs.
Thank you. I'll try out all the things.
Must be one of them.
Fingers crossed.
All right. Well, welcome back, folks. I want to talk today about, I want to talk about dexterous manipulation, as it says on the screen. Working with more dexterous hands, but it's also kind of an excuse to talk a little bit more about planning through contact and thinking about planning and control through contact and the implications of that being one of the big reasons that we're still struggling to do dexterous manipulation with complex robot hands. Okay, so last time Naveen talked about tactile sensing. That was awesome. Before that, we had talked about trajectory motion planning first, and then reinforcement learning. I threw in a little bit about adaptive control. So when we talk about now, how would you apply the tools we've got from motion planning and reinforcement learning, for instance, to the idea of a much more dexterous hand? That's what I'd like to sort of think through today. And there's actually a fantastic number of robotic hands out there. Oftentimes people will say, well, the hardware is the limitation. We don't have good enough hand, or we haven't solved the dexterous robotics problem yet. But there's some really good hands out there, right? And this is just a quick snapshot, but the shadow hand is maybe the one that's become very famous from like the OpenAI Rubik's Cube, which we'll talk a little bit about. The droid hand is famous from being seen in all the Mujoko simulations. The Allegro hand is a fantastic lower cost, more servo-based hand. The shadow hand, for instance, is very expensive, but the Allegro hand is much more reasonable. The Robonaut hand was like a beautiful hand even 10 plus years ago, but the list goes on. And if you're watching for these, they just keep appearing. Some of my favorites I'll show at the end. So there's a lot of like really beautiful robotic hands out there. This is the Adroit hand, from Mujoko. This is one of my favorite examples of it, where they're doing some pretty complicated tasks, like picking up the hammer. In this paper, they actually recommended a handful of these tasks as benchmark tasks for dexterous manipulation. And I think the ability to simulate it and control with a full complicated dexterous hand is still an open problem. The fact that they can do as much as they did in this paper is just absolutely awesome. But we still have a ways to go to make real robots someone actually choose to use a big, complicated dexterous hand on their robot. There are reasons why you would pay that price in complexity and cost if you could do more tasks, but we haven't completely solved the problem yet. I like to put in some of the history, right? So it's not a new thing, right? This is Ken Salisbury, who he did this, I think, just before he came to MIT, but this robot was upstairs at MIT for a long time when Ken was here. In fact, you should look at his biography. It's just awesome, the number of things he's done and been involved with, maybe after the lecture. But there's a link there that you could open up and set aside. But this is, like, you just watch what this thing's doing. This is choreographed, of course. It's not solving the planning and control problem, but that's a hand from 1982 doing like bottle twisting and everything, right? It's absolutely incredible. And it had, if you were to look at the side view of the hand, right, it's got motors, a bank of motors off to the side, and it's cable driven. But just absolutely beautiful, stunning hardware. How many years ago? Almost 40 years ago, right? So it's hard to blame the hardware, I think, for why we haven't done better. I showed you this like in one of the first lectures, but it's like my favorite robot ever. This is the high-speed hand from Ishikawa. In fact, like whenever anybody like at a conference asks me, right, what's your favorite robot ever? And I have to put it on my name tag, I always pick this hand. It's just so incredibly good. Like what they do with this is a 3-fingered hand. This is the same foveating tracking that I was talking about for Jean-Jacques' catching maneuver. It's got tactile sensors too. Okay, but then it's just sort of ridiculous what they can do with this hand. Pen spinning, I mean, it doesn't last a super long time, but it's just awesome, right? I mean, again, there's like control issues to solve, but the hand is just awesome. It's overclocked. I think it would melt if you left it running too long, probably, but it's so good. Okay, and this was the that hand solving the Rubik's Cube in just the. Okay, so I would argue that the hardware is not the major limitation keeping us from having really dexterous robots using human-like hands to do complicated tasks. So what are some other possible? I mean, the cost and reliability of those hands, I think, is still a bottleneck. So it's hard for everybody. Maybe if enough people had those hands in their living room and that was fine, then the field would be farther along. But the hands definitely exist. I mean, dexterous hands have turned into a pretty big motivation for reinforcement learning, right? So right, it's been sort of one of the key challenges in manipulation is to show that you can do something with a dexterous hand, because our more classical approaches haven't done a good job of solving that problem. And the argument goes a few different ways, but one of the reasons that people started doing this initially, they said, for instance, the hand is just too complicated, right? So meaning that, first of all, the argument for reinforcement learning started with we don't have good models, right? People said, maybe for an arm, it's okay you'll get a reasonable model of the friction in the joints like we do for the EWA, enough to do sort of model-based control through that, but you're never going to be able to model all the stiction and complexity of like a hand. And those things at that scale sort of would dominate the dynamics compared to the the inertial effects are small relatively, and the friction effects are large. So that was actually one of the big arguments, I would say, for why people said, therefore you need reinforcement learning. I think the bigger thing, I think you guys, I've said it enough that you know that I think the bigger interaction that we don't understand is between the hand and the world, and or the objects in the world. I think that's where there's lots of uncertainty. But I would actually argue that we have a pretty good model of the hands. People also argue that just the complex context scenarios are too hard to simulate, right? But I mean, I don't buy that. So I think, first of all, many of the successful RL approaches have been in simulation. And like the OpenAI one was explicitly about saying that we trained in simulation and then we moved it to reality, where they closed the sim to real gap, right? And in general, I think that the simulations are good enough. The big question is certainly they're accurate enough. The biggest question in my mind about simulation still is whether we can simulate the diversity of the real world. But if you want to say, can we accurately simulate a single hand and the way it interacts with a Rubik's Cube, I think we definitely have a strong enough set of tools for that. There's a bunch of people that will argue that simulation is doomed to succeed. That's a famous quote from Rod Brooks, and it gets used often. This is just to be provocative or whatever. I don't know. I think the people who say that don't know how to use simulation. Sorry to everybody, but really, I think simulation can be misused. You can run simulations that are narrow and it will succeed easily. But if you add enough robustness and uncertainty and show robustness in simulation, then it has all the power of sort of robust control and the like. And I think a well-used simulation can be used extremely effectively to transfer to the real world. So just to make the point, though, well, I'll wait a little bit on that. Okay. So I don't buy either of those solutions. I do think there's some amazing things that RL has done to show progress in dexterous hands, but I just don't think those are the main arguments that justify it, or those are the reasons. Right. So if we, I'm going to sort of find a red pen and say I'm going to say no to those for now. So if we agree that we have a good enough model, right, and we agree that we could use simulation, nobody's actually agreed, but I'll just take quiet as acceptance. Then I still think there's a fundamental challenge that's blocking our more widespread adoption of dexterous hands, and I think the planning and control through contact is still hard. We don't have good enough solutions there, and that's sort of on me. That's my field. So everybody else has been successful, and our part of, we're not holding up our end of the bargain. So so let's talk through. I want you to sort of understand why I think that. What's the difference between the planning and control that we've said has been very successful, that we've used so far in class, and why am I saying that suddenly, if I've got a dexterous hand, isn't a dexterous hand just a more complicated robot? If I said we can do planning and control for Atlas, how can I say we're having trouble doing it for a dexterous hand? Right? So let's recall, my presentation of motion planning was, I said, if you understand inverse kinematics, then you are pretty close to understanding motion planning, because you started off by writing rich constraints, saying I'm not in penetration with things I don't want to be in collision with. I'm accomplishing some task by being in the right kinematic configuration. Maybe my head is looking at it right. The richness is in specifying these constraints. once we have constraints, then we could, motion planning was really just listing a bunch of constraints along a trajectory, right? Where you have IK constraints on a lot of these different points. For collision-free motion planning, that was enough. When we wanted to pick something up, for instance, right? If we wanted to just, reach over, I don't know why I got so out of focus there, but the camera will figure itself out. If I wanted to reach over and pick something up, then I can solve a slightly more complicated motion planning problem where I'm going to sort of reach over. I have one set of trajectories that gets me here. I'll close my hand, and then I'll assume that the mug moves with me. So I've got an additional set of constraints. For instance, I don't want the mug to smack into my keyboard or something, and I move through the air. I'll set it down. Okay. So in that case, for actual manipulation, I was writing. We were doing something called multiple shooting. Where we'd say, here's like, the move to mug here with a bunch of different constraints that were just constrained to be, near each other on a trajectory, for instance. And then at time pickup, I would close the hand. I'd have a different trajectory. Let me even use my color palette here. Okay. This is now moving with mug, right? At the point of intersection here, I added extra constraints that the hand was in the same, was in a reasonable configuration next to the mug at the final constraint of that first trajectory. And then I weld the mug effectively to the hand here, and the mug moves with the hand during this trajectory. And then I could, for instance, set down. And solve my, move away trajectory. Okay, so this was just a bigger optimization problem, just like the inverse kinematics, where the constraints I've added are different in the first segment, different in that middle blue segment, and different again. And the big difference in the middle blue segment is I said the mug should be attached to your hand during that time. So implicit in there, the way that we cheated when we did that was we preordained when the contacts were going to happen, like how many points, like at which sample points were we going to be in contact, and at which sample points we weren't going to be in contact. So this was a predetermined, we tend to call it a contact mode sequence. Okay, and here's what happens when we've suddenly got a very dexterous hand and we want to do something like the OpenAI cube twiddling the Rubik's Cube or something. Even if I want to think about now more subtly the interaction between the fingers and the mug, I can't specify, I should not try to specify which part of which finger touches the mug at what time, right? Like the contact mode sequence, if I zoom into at a level of detail to do more dexterous tasks, gets ridiculously complicated, ridiculously fast, right? If I had to say, I want my first, first link or my last link on my first finger to touch, and then my middle finger, and whatever, that's just not going to get the job done, right? It'd be fine if you were a little bit wrong for something like a simple enveloping grasp, but if you want to do, something more complicated like twiddling your pencil in your fingers, it gets very, very hard. Okay, so the fundamental problem that we need to address to do planning and control through contact more generally, which is the problem that Dexterous hands presents, is to solve for the contact mode sequence, to try to find a motion plan that doesn't require the human to pre-specify the contact mode sequence. Is that clear? Yeah. Okay. So there are a few ways to do that. It's still going to look a lot like what I've drawn here at the top of the screen. But I want these constraints to be in for instance, the mug being attached to the hand. Can I make that a variable somehow, a decision variable that could be turned on and off at any potential part of the trajectory, with, of course, consistency constraints that somehow make sure that the mug doesn't become attached and unattached in the middle, right? So somehow I need to make, to solve the contact mode at the same time. So I would actually say there's two broad approaches. One of them would be to lean even more heavily on simulation. So if you were to just try to ignore the constraints on the mug and say, all I'm going to optimize is for the commands I send to my robot. I'm going to run a simulation. I'm going to do, I'm going to just put a reward, for instance. I'm just going to define success of my motion plan as minimizing a cost with no constraints on the mug location or whatever. Then you could sort of just simulate your controller, maybe try to take gradients of that and optimize directly. So you could, right, this is what RL is doing, is you're just going to take, if you were to try to optimize a trajectory with reinforcement learning, you would just write down the parameters of the trajectory, you would run simulations, you would try to optimize some cost, okay? If to use some of the stronger tools for motion planning, the question is, can you take gradients through the simulation? And I want to spend a few minutes talking about when you can do that, when you can't do that. I think people are, I see a lot of confusion in the literature about how hard that is to do and when you can do it or why it's hard. The other thing you can do, which we'll talk about also, is add somehow the contact decision as decision variables. So you can explicitly ask your optimization to control find me a trajectory where the mug may be attached or not, like I sort of said, I talked through before, and I'll give you details about that in a minute. So I think it's an important question about whether we can expect to take gradients through contact. And it's not just about whether you should be using gradients in your optimization. You can do reinforcement learning and do sample-based gradients, or you could do, sort of analytic gradients. But in either case, if you're trying to do a policy gradient type approach and the gradients are discontinuous because of contact, for instance, then it might challenge even a gradient-free method that's trying to climb down a landscape, right? So I'd like to just think with you a bit about what do gradients look like through contact? And I guess I made a note to myself. I'm talking about more of the motion, the trajectory optimization version of motion planning. There are also sample-based approaches to motion planning that I could have made as an option 3, but I don't want to try to cover a little of everything. So I won't talk about those today. But of course, there are things that look more like an RRT or a probabilistic roadmap that could help you with planning through contact also. Okay, so what do gradients look like through contact? So let's try to keep it simple so we can think about it. Imagine that problem of flipping up the box like we did in the force control. Right, I like that one because it was my Cheez-It box, my blue finger that I was applying a force here. Everything was reduced to a point finger. The equations of my motion for the finger were simply mq double dot equals u plus my contact forces. The box has similarly simple dynamics just in terms of its x position, its z position, and its orientation, okay? And what I want to think about is if I'm going to execute some trajectory with my finger, if I change that trajectory a little bit, how much does if I change, let's say, the initial conditions or the command of my trajectory over time, a little bit, right? If I make an epsilon change to my command, do I get an epsilon change in my trajectory out and therefore my reward out? That's like the fundamental question, is how much discontinuity is coming in, and this how much is our contact's going to break our gradient-based optimization. Okay, so in fact, I can go even simpler, I think. It's like almost the same problem, but I want to just zoom in on that initial point of contact. So let's think of it as throwing a ball at a wall. It's the sort of the classic contact problem. So I'll take my blue ball, I'm going to chuck it at the wall, okay? And I'll assume, for instance, that I'll keep things simple. I'll say the contact in this case is elastic. It'll bounce off the wall, not stick to the wall. So it's a rubber ball, not a putty ball or something like this. I'll assume frictionless contact, although that it's not too much harder to add that, but just complicates my simple example here. So the reason I like this sort of throwing or smacking a puck or something like this is it's a little bit more, because it's a little bit more ballistic, is I can reduce my control decisions, if you will, down to just a few parameters. So let's say that the only thing I get to choose, I'm going to always throw the ball from the same location, but my control decision is what's my initial velocity, right? So I'll call it x dot at time 0 and z dot at time 0. And then the fundamental question I want to ask is, ultimately we're going to have some reward function that looks at the trajectory and tells me whether we're doing a good job, okay? But let me just sort of, I'll keep it even simpler. Let's say that the reward only depends on where x is at time 5. So it's a finite horizon problem. At time 5, I'd like the reward, I'd like the ball to be in some region or something like this. I've got a target location. Okay, so I think it captures a lot of the problems we're talking about. If we were to just say, for instance, what is, let's say, partial x5 for a change in the initial velocity? Right, if I were to make an epsilon change in my only control decision, do I get a smooth change? Like what happens to my change in the position of the ball at time 5? Is that is that gradient well defined? continuous? Is it discontinuous, right? So let's plot a few things here. First of all, let's plot x dot at time t. So x is just my horizontal position, and I'll make it as a function of t. Okay, so what is this thing going to look like? So I've got it. I'm saying if this is my coordinate system is positive x here, positive z there, then I'll say, you know, if I start off with some initial velocity, there's no wind resistance. I'm going to proceed with a constant velocity until the moment where I hit the wall. And then I'm going to bounce off it in the opposite direction. Right? That's what x dot looks like. So absolutely, most contact models, inelastic, elastic, whatever, you are going to see discontinuities. T's in velocity at moments of impact. Depending on how you modeled it, if it was a softer collision, there might not be an actual strict discontinuity. It might be that you're loading up a spring, but it'd be a very sharp change in that trajectory in velocity. Okay, and then you know, this is the time of collision. Right here, right? Okay, so what if I were to change my initial velocity a little bit? What happens? So let's say maybe I do x dot, my x dot nominal plus some delta, right? Let's be a little careful here what happens, right? So I'm going to continue with a constant velocity. I'm going to hit the wall earlier. Let me exaggerate it a little bit. But I'll hit the wall earlier because I was going faster, right? And then I'll leave with a larger velocity. You agree with that? But what I want you to understand is that there's an entire continuum here, right? If I make delta arbitrarily small, I can sort of close that gap, right? A small change in here will ultimately lead to a small change in here, even though it's going through this discontinuity. Small change here will lead to a small change here, whatever. The whole thing is going to, my final velocity is still going to have a small change. And in fact, I could move this up and down and expect certainly in the final velocity is going to be fine, right? If you try to take a gradient in here, you're going to see numerical challenges, but actually the long-term behavior is pretty good. Is that clear? I mean, I tried to pick an example that was simple enough that everything makes sense. Like it should be transparent. So please ask questions if, you know, do you realize, see I got a bigger bounce, right? If I have more velocity coming in, I'm going to leave with more velocity coming out, and you know, everything should make sense, I think. Okay, so what does x of t look like? Actually, I should I've drawn everything on the negative side of the wall. I'll make the wall at 0. So let me do it like that. Okay, so what does x of t look like? Well, again, I mean, x dot of t until I hit the wall, it's just t times x dot 0. When I hit the wall, I'm going to just instantaneously change velocity. So you can solve it out. So in the case where it hits the wall, the time of collision looks like something like this. And if I were to figure out what's x5 for the cases where I've hit the wall sometime between 0 and time 5, then my total solution looks like -5 which is actually -x0 minus 5x dot 0. So basically just making the point that I can solve everything completely. And what I get here would be if I started at some initial negative x because I'm to the left of the wall, I'm going to go up until I hit the wall. I'm going to go down. And my rate is always going to be the same here. This is my x dot 0 is my slope, right? And similarly, if I were to make a delta change here, now my slope is going to be a little less steep because in this picture, if I had, I'm sorry. If I were, sorry, I could keep the slope the same even if my x dot is the same, but I'm going to hit this a little earlier. If I started a little closer. The point is a small change here, even though it's bouncing off the wall here, is going to be a small change over there. We agree?
Shouldn't it be starting at the same position and have a slightly different slope?
I could do that too, right? Oh, you're right, because I wrote the partial. Let me do that. That's better. This would be a change in x, but you're right. I promised to take derivatives with respect to x dot. So if I change x dot a little bit, I could go like this. And it would come down at a sharper slope too. But the smaller I make in that change, the closer those points will be, and eventually the closer these points will be, right? There's nothing that causes instantaneous, there's no small change there that makes that fundamentally discontinuous. This was x0 plus delta, and this is x0 with x dot 0 plus delta. And even if I were to go ahead and plot all the way to as a function of x5 as a function of this, which is what my cost, which is my surrogate for my cost here, right? We have the equations up here, right? In fact, again, I should have drawn it up there. Even x5, the final solution, it's a little bit more math, but which is up there. But again, the solution is actually simple. There is a discontinuity, right? Which is happening here. These are the solutions that don't hit the wall before time 5. These are the solutions that are after hitting the wall, okay? But it's actually a very well-behaved object. So I think people talk a lot about the complexity of making collisions as causing difficult discontinuities for optimization. And there is some truth to that, but it's not here in the math. The math is clean, right? This, this sort of thing actually is a complication, and it's even more apparent if you look at Z, for instance, right? If I were to plot the change, let me plot x5 as I changed, this is as a function of x dot 0. If I were to change it as a function of z dot 0, then actually I would see something very different. My x5 would start by bouncing off the wall, and that at some point it would look like this. This is my long-term dynamics, because there are some trajectories, of course, there's a difference in the trajectories that are like this and a neighboring trajectory that just keeps going like this. And that sounds like I'm just kind of dwelling on something that's obvious, but that is fundamentally the hard part of the contact problem, is not that you make contact with an object, and the way that you make contact it is hard. The only hardness, I think, really, the fundamental complexity of contact is whether you make contact or not, okay? And that causes massive discontinuities and massive rifts in the optimization, and it's hard. But just making contact is not hard.
There's the question on the chat by Antonia.
I think you answered it at this point. No problem.
Yeah, I'm sorry that I didn't see it soon enough, but yes, absolutely. The point is that that the dynamics when you're in contact are simple. It's only making or breaking contact. Okay. It's even, so it's sort of like more important than that, right? So if I'm taking a gradient paste method, if my goal is to put the ball over here, and let's say I have to start throwing the ball this way, I've got some constraints and you can only use positive Z. I'm shooting a cannon, it's pointed this way. I can tip it up and down. Okay. If my current trajectory is over here, and you're asking the optimizer to find the solution that's over here, there is nothing about the gradient information on this trajectory that tells it any information about if I come down here, something fundamentally different happens and it'll move this way. Okay, that's, I think, the missing challenge. If you're doing local search and you're not making contact, then there's no information for a gradient-based approach to know that it could go into contact to solve the problem, unless you do more. So the richer approaches to planning through contact have to address that problem. Okay, so this is the math. I think the math is actually very clean. The numerics get a little bit more complicated. To the point where they have a massive influence on whether your algorithm is going to work or not. Right, so for very simple models, we actually do, in this case, I was able to solve for the time of collision with algebra, simple algebra. And then I could do the integral up to the time of collision because it's trivial, and write the solution in closed form. For simple robots, where we've seen lots of success of trajectory optimization through contact, oftentimes we still do that type of numerical work, where we, even if we don't know where the contact is happening beforehand, if we haven't preordained it, we can simulate forward. If a contact happens at if I'm taking big steps in my simulation, discrete steps in my simulation, and I can tell that something happened between this time step and the next time step, there are good numerical recipes for backing up and finding the exact instant in time when that contact happened. And you can do arbitrarily accurate simulation through contact. Okay, and if you, like the story we talk about in my under-actuated class of simple robots, of passive walkers and the like, and walking robots, this is what we do. We actually do careful event detection. To solve for the time of collision, and then we can take exact gradients saying how much did the time of collision change, so that how much does that change my integral coming up to the collision, and how much does it change my integral coming out, and everything is clean and good. Up to numerical precision, roughly. When you get simultaneous, and there are cases that are still, worthy of writing new papers and the like, where, if you have simultaneous collision, you have to define a directional derivative. There are details that people still work out, but the basic story is simple. Now, I can't say it can't be done. I won't say it can't be done. In fact, I think we should just do it at some point. But nobody, to my knowledge, has actually written a simulator that does that at the scale of a dexterous hand. Okay, for performance reasons, for complexity of writing the algorithm reasons, Yeah, I think I can't. There might be one contender, but it's like atoms, or it's not like Mujoko or Piebald or anything like that. So if in practice the robots, the simulators that we're using in robots are only doing either stiff numerical continuous simulation or time stepping simulation, right? And we do both of them in Drake. So you've seen both, for instance. We either do continuous time models, for instance, with stiff springs, for contact, or these time stepping models, which we've talked about. Okay, each of those bring their own challenges to the trying to estimate a gradient, or just asking how well or how consistently trajectory optimization or reinforcement learning will work through your simulator. Okay, the problem with stiff springs are great in the sense that I've made my contact continuous. So in some sense, I've smoothed out the discontinuity even in my velocity curve. But do people know what stiff differential equations are? It's not a coincidence that they use the same word, but these result in stiff differential equations, ordinary differential equations. A stiff ordinary differential equation is one, there's a couple different ways that people define it, but it's basically where there's a variety of different time constants underlying your dynamics. Often it's even simultaneously. If you have some things that have like a time constant which would ask you to make a very small simulation step, and other variables in your differential equation that would ask you to make a very big time step, then that becomes a numerically challenging thing, because everything is going to be squished by your requirement to be very accurate on a few variables, even though you'd like to be able to simulate in big steps. Similarly, if I have a robot that's moving through the air, where I could take very big time steps, and then I have to somehow take very, very small time steps. That's the fundamental problem. It's just that at some point, in order to simulate a spring that is a reasonable stiffness for like the wall, I'm going to simulate a stiffness of 10,000 newtons or something like Newton meters or something like this, and that's going to require itty bitty time steps. And if you want to do itty bitty time steps in a trajectory optimization, then you need lots of decision variables along your trajectory. And taking gradients is going to take a long time. Simulation is going to take a long time, potentially, if you simulate accurately. And computing the gradients is even more expensive. So, very expensive. And when you start cutting corners, dangerously inaccurate sims. Okay, especially the getting the nominal solution out, you'll see high sensitivity. Like if you were to take your trajectory through one of these stiff simulators and you're simulating it at a rate that you're pretty happy with, you change the initial conditions a little bit, you won't see this beautiful, smooth, small change in the output. You'll see things jump around and be bouncy because the numerics, you're probably taking slightly too big time steps at the moments, at those stiff moments. We do have error-controlled integrators in Drake that will just slow you down so that it's accurate. But still, if you set them as accurate as you'd really like to get smooth gradients out, then you'll be unhappy. The time-stepping models have a different problem. They again are, you can take gradients through all of these things, but they are now discretizing time, and actually you can take gradients through. I just think people don't often do it carefully enough. And the other thing that happens in both of those models is that once you're simulating with any penetration, then all of the complexity gradients of the surface normals when you're in penetration. Do you remember that example that we worked through before? Where once you're in penetration, the normals are looking like this, and then they flip and they move around. All the complexity of the collision engine gradients comes into your problem. And that's real, not like I say, that's real if you're doing a 0th order RL type method, and that's real if you're trying to take real gradients. In practice, it's hard to simulate these things accurately enough that if you take a very small change in the initial conditions, you get a very small change of the output, even though that's what the physics would tell you should happen. So there's a couple sort of, I think, more fundamental approaches to getting around this. Let me talk about a few of them. Okay, so how do we? The complexity of the collision engine, you know, that one of the things we're trying to do for this is to try to use these hydroelastic models, which I've showed you before. I could say that is a fundamental approach to trying to improve the numerics of dealing with contact when you have penetration. That was when the pictures I've showed you before of trying to do, instead of point contact on point contact, you have a volume contact on a volume contact, mesh on mesh, take a surface integral, much more complicated operation, but it fundamentally addresses some of the challenges of the collision geometry gradients. Okay, so that's one part. There's another thing, this is maybe an aside, a rant, if you will. I'm getting older, I have too many rants now. So a lot of people say, I'm going to take my ugly simulator, right? It's got maybe bad gradients, or I can't get the gradients out of it, and I'm going to generate a bunch of trajectories. I'm going to fit it with a deep neural network, and now I've got a good model, and the network's going to protect me from this. I don't see the logic in that. I just don't see how that makes it. I mean, I think it is convenient to ask PyTorch for gradients. There's no doubt about that. But if your simulator is not giving you consistent, accurate results, fitting it with a function approximator, if it's a good function approximator, it will give you the same bad results as the simulator. If you say it's that the simulator, if I just want, I don't know, I just don't see any story where that makes the problem better, right? In my mind, maybe if it's just really about using PyTorch and not having to write the gradients directly, then I guess that would be okay. But I think that you're only incurring complexity and uncertainty when you could just write the gradients. Sorry to those people out there that are doing that. Okay, so there is a fundamental approach, and I think RL nails this one. Is to change the objective. So far, when I've been talking about motion planning, we've been talking about minimizing our long-term cost. You know, something that is, maybe we've been optimizing Q dot instead of thinking of it as U, but we've been thinking about this sort of objective, right? And I'll just be super clear. This is some running cost where I have a sum over N. Those have been the objectives. But in RL, we change to a stochastic optimization. Where this is the expected value that's taken over, let's say, initial conditions. Over maybe the size of the box, inertias, right? You can put zebra texture maps, people do all kinds of stuff, right? And I think there's something really good about doing all that. I'm not from zebra maybe, but it can fundamentally change the problem, okay? I think this is something RL definitely has gotten right. So how does it fundamentally change the problem? If I go back to my wall example, RL isn't the first to do this. I mean, we've known about stochastic trajectory optimization forever, but I think people didn't push it hard enough, and RL did. Right. So now, if I have my nominal velocity, let's say, but I actually have let's say a distribution of initial conditions. So let me draw the level sets of a distribution by saying somehow I'm in kind of some set of initial conditions here. There's uncertainty about my initial conditions. Then what's happening here is I'm going to send let me make my wall a little taller, just so. Okay, so I'm not going to send just one trajectory over. If I'm sampling this, I can actually think about it as I'm going to send sort of like a volley of trajectories over, right? And the amazing thing, each one of those is well behaved or whatever, but some of them are going to go over, some of them are not. If I look at my plot, for instance, of which one did I draw here? So if I change, let's say z dot nominal 0 here, let me call it like this, and I say that z0 is z0 plus some Gaussian random variable. And I plot now the expected value of x5. Whereas my nominal thing, I had a solution that looked like this, where for small x dot zeros, I was hitting the wall and bouncing back. For larger ones, I was going forward. If I think now if I change z dot 0, let's even say this z dot 0 here, then I really will do something better, where at some point, some of my arrows, some of my balls are going to start going over, some of them are not, and eventually all of them will go over, and I can smooth out my contact, right? And if there's a Gaussian that has an infinite tail, for instance, then it really does, that means that even when I'm in this case where I'm shooting over the wall, if my nominal my nominal trajectory somehow is shooting over the wall, but I've got enough randomness and expected value computations, then the tail of my distribution is still telling me there's something that's happening down here, and my gradient tells me that I should move down in order to make contact, in order to pull this way. If you remember one thing from the lecture, I want you to understand that. I think we've known that stochastic trajectory optimization is like a better object in some sense for a long time, but I think RL is the community that sort of embraced using Monte Carlo approaches to this. More so, I mean, okay. There's someone out there who does stochastic trajectory optimization with Monte Carlo for 40 years, and they won't like me saying that, but I would say the massive trend happened, where I would say using massive Monte Carlo sim. to approximate those expected values, because computing the expected values through contact in a closed form way is hard. So if we look, for instance, at the OpenAI Dexterous hand, right? So I think people know this, but it's I actually really like the paper and the work. I think they threw compute at it big time, and they're perfectly honest about it. And you know, they basically had the simulator twiddle its fingers for the equivalent of 13,000 years, right? And it's a big AWS bill, or whoever's paying the bill there. That's a lot of compute. Raise the temperature of the earth a few degrees or something, you know, but it worked, right? And it solves a problem that we weren't solving before, right? Because I think there's a few other things happening here. Of course, there are deep networks in the policy, although not deep. That's another rant here. Is I think most people who are talking about deep RL use like 2-layer networks. So I don't actually think deep RL is deep most of the time. If they have a perception part, sure, but the policy is normally not. Okay, but maybe it's the fact that you're doing policies instead of trajectories. I think that probably does matter a little bit, or that's different, but I think more work is required to understand the differences about what the landscape looks like in policy, different policy parameterizations versus, let's say, a trajectory parameterization. If I had to put my money on it, I think the thing that's fundamentally different is that we're smoothing gradients by doing randomization and smoothing that landscape. I do have one beef with the paper, right? It was, you know, solving Rubik's Cube, like we're done, right? And if you look at the results, right, the final results, the thing that drives me crazy is like, I look down and I'm like, okay, success rate is 20% and then 0. And so that kind of bugged me. But then I'm like, why are all the numbers so round? And then it's like, oh, they only claimed success for 10 trials ever. So it worked twice, like ever, or like they reported twice. So anyways, that's if they can spend that much money on simulations, they could have reported a few more experiments, I think. So, okay. Good. Get myself in trouble here. So I guess I want to make the point that I think there is a difference. They think of things searching for policies, not trajectories so often. Of course, there's a continuum. So I would think of a list of commands over time as being, you could call it a policy, but that's a trajectory. That's on, you know, a trajectory is a limiting case of a policy where I've just got an open loop set of commands. There's a policy, which I could think of as, it's a function that tells me no matter where I am in state, what action should I take, as the other extreme. There are also sort of in between things where you can do trajectories plus, let's say, a feedback gain that you'd expect to be a local policy. So I think there is a big deal. There is a big difference. I think we already know there is a big difference when you're doing stochastic trajectory optimization to optimizing closed loop trajectories. Versus open loop trajectories. Right, so if I ask what happens to just an open loop set of commands when I've got lots of randomness, things might diverge. I might get a very different answer than if I know the way I'm going to execute a trajectory is by closing a little feedback loop around it. You should include that in your optimization, because that will, you know, the distributions that might have expanded in an open loop can compress and give you a very different answer Okay, so that is a big difference. And I think when you switch to doing stochastic trajectory optimization, you should if possible, do closed loop trajectories. And then what I was saying about, I think, the difference between policy parameterizations and trajectory parameterizations. I think we need more work. I think you guys should do that work. It's maybe the next big thing we have to figure out. When does, what are the right policy parameters? I mean, I think convolutional networks seem like a very good choice for images. I have not seen as compelling of an argument for problems like this. And I think there are parameterizations that are going to make more sense. We should be able to understand, we should understand sort of when they're going to converge, when they won't converge. To make an analogy to the deep learning for perception, I think, or for supervised learning more generally, there we've talked once before about the overparameterization story, right? There's somehow a little bit more understanding now of why, if you're in the supervised learning case, that might be a reasonable, that you have a reason to expect the optimization to converge. But we're not in the deep overparameterization. I mean, I don't know, we don't even know exactly what it would mean to be overparameterized for a policy like this, but we're not in the super big parameter regime here. So I don't think there's any comparable story like overparameterization for feedback. Okay. The other big approach is to sort of tell the optimizer about the discontinuities. Right, so if my optimizer is somehow currently considering trajectories like this, you'd like to somehow give more information. There are a couple different ways we'll say more information that lets it know that you could have hit the wall if you chose something slightly different, even though you're considering this trajectory right now. Okay. Let me show the one way to do that is to add contact forces as a decision variable. I know at least one group is working on some results from a paper by Mike Posa in 2014 that does this. So the way you would do that is you would effectively write the dynamics as your constraints between the sample points. Okay, but in order to tell the solver that you can make contact or you don't have to make contact, you actually add forces as a decision variable, and then you add complementarity constraints. Which basically say that your contact force has got to be greater than or equal to 0. The distance, my contact distance, has got to be greater than or equal to 0. And then one extra constraint saying force times distance equals 0, which is, you could read as saying force equals 0 or distance equals 0. And then by moving effectively your time stepping algorithm into the optimization, into the constraints that you've written that bind the different points together, and making force an explicit variable, the optimizer, in order to satisfy the dynamic constraints, in this case, has to set those forces equal to 0. but there's a gradient. It knows that if the force were to go up, it could move the trajectory this way. And it knows in order to pull the force up, the distance needs to go down. And there's a signal that would allow it to understand that it could pull itself into contact in order to go back. There still could be awful local minima, but at least the information is provided to the solver in this sort of potentially hard way. In fact, it's a really nasty constraint. So if you were to think about what that constraint looks like as an optimization problem, if I have force and distance, I'll write phi of q as my distance here. I should just write distance. This is like not a good constraint to hand an optimizer. It looks like this, right? It's like I'm either on this axis or I'm on this axis. If I couple it with those, it's in the positive axis, right? We like convex constraints, things that if I have 2 points that are in my constraint set, then the line between them is in the constraint set. This is like the worst form of that. So there's a couple ways that we work on doing that and making that better for the solver. We can relax the constraint. So this complementarity constraint is bad, but we can relax constraint. There's a few ways you might choose to do it, but one way we do it is something like this, where we say, for instance, that force times distance is less than or equal to some smallish number. Maybe it's a not so small number to begin with, and we let the solver find a solution, and then we make this parameter smaller and smaller and smaller, so that approximation gets tighter and tighter and tighter until it, in the limit, becomes this. Okay. What does that do? What is that doing physically? When I'm on a solution or when I'm considering trajectories over here, it's allowing me to have force at a distance. It's allowing me to say, you could, even though you're not touching, there's some, so not touching, my distance is not zero, but I'm still allowed to have some force. Okay, so it can start contributing force and finding its way towards this problem, these trajectories sooner. It's numerically better. Yeah, okay. The other way that I like to do it, is when I see a constraint like this for an optimization problem, that sort of begs for disjunctive programming, which comes down to being, you could write it as a mixed integer optimization. Mixed because it's both, it's got some integer variables and some continuous variables. And I won't jump into all that. I just want to point out that there's another way to write these problems where you actually say, you have a binary variable. In fact, you can add a constraint or add a decision variable that's binary. You'll see this in mathematical program in Drake. You can new continuous variable, but you can also say prog.new binary or integer variable. And you can make a different variable which says I'm in this regime or I'm in this regime. And that makes the problem something you can express with binary variables, but otherwise convex constraints. And we have explicit optimization approaches that think about how to balance, how to search, for instance, with branch and bound and other things, how to search through the binary decisions while solving the continuous decisions. We continue to work on in my group on mixed integer optimization approaches, although they're going to look a little different. The next round, we got some good results coming out soon, I think. Tobia, if you're out there, no pressure. But I think there's good things coming out here, but they're going to look a little different than what we've put out before. They're more approximate solutions to to the strong mixed integer formulations. Good. So I guess that I don't want to say a lot more about that, but please ask questions if you have them. So does that sort of level of understanding provide some insight, right? The fundamental problem is not contact with the object. It's when you change contacts. I think the two fundamental approaches I've told you so far here are go to stochastic or somehow tell the optimizer about the discontinuities. And those then can allow you to solve the problem which we didn't solve before, which is to allow the solver to determine when you're in contact and when you're not. So I think robot hands will get better, but they're not the bottleneck, not right now. I mean, maybe their cost and reliability makes it so, like if everybody had one, would things be better? Probably. So maybe there's a bottleneck there, but in terms of like, if you have all the tools and you want to get it done and you can afford a robot hand, the robot's hands aren't stopping you, I think. Simulation will also get better, but I don't think sim to real is the bottleneck, not on the hand part, maybe on understanding all the different things the hand has to interact with. But I think we fundamentally need more progress on planning and control through contact. If the changes do not, for changes in parameters that do not make or break new contact, gradients should be well behaved. You just have to be careful with your numerics. But for making and breaking contact, changing whether you're making or breaking contact, you need either stochastic optimization or contact implicit, mixed integer being a form of contact implicit. Okay, let me end with a little optimism here of there are good hands out there already, but they just keep coming and they look so good. And I said the robustness might be an issue, but like people are really hammering on robustness, right? I think in a minute they will actually take a hammer. I didn't mean that as a joke, but they can do pretty complicated things, and yeah, I think they're really getting much more impressive in terms of robustness. Now, oftentimes I don't actually I haven't found a paper on this one yet, or maybe I just haven't read it yet. But if I look here, it looks like there's not a lot of proprioception in the hand yet, and that's another thing that you would add and get. See, there's the hammer. There's another that that would add more complexity and maybe challenge robustness and everything. But I think there's every reason to be optimistic. If you want more dexterous hands, you should build them, or you should just wait a little while and someone will build some awesome ones. I also think we shouldn't be obsessed with human hand. There are all kinds of clever ideas waiting to be discovered of slightly different hands that are going to do awesome things. This one, the new degree of freedom, is just a roller on the fingertips, right? And it's like such a good idea. I mean, I've heard people talking about this for years, but I've never seen it until recently with Mark. This is not Mark. This is Ken Salisbury again, same one who did the one in 1982. It's good. It's beautiful. Like, it's beautiful. You can watch what it does, and it's really good. So be creative. Suction's okay. Use suction if you need to. Use widget fingers. Whatever you need. It's a hard problem. Okay. I do have a survey. Where did it go? Please answer the survey. I screwed up. I don't know where my survey is, but I'll send it on Slack, or on Piazza rather. Any last questions? Everybody's so quiet. I hope you had a good Thanksgiving at least, but are you recharged a little? Yeah? End of term crazies?
So
Well,
what
I'll
was
hang out for a
the,
little bit. Oh,
oh,
what's that?
sorry.
Oh, good.
What was the limitations of using either the stochastic approach or using mixed integer or relaxed complementarity? Because those all sort of seemed like solutions, but you said there's still a lot of work to be done in those areas.
Yes, fair enough. I think the answer is a little different for each of them. So the stochastic adds some signal which allows me to sort of smooth some of the worst, if I'm near contact, I can still discover making contact. But there are still many local minima in the optimization problems that we write down like that. So we don't have, I think even the great simulations and RL and trajectory optimization that we see, a lot of times we don't see that it took a lot of random initial conditions, a lot of random guesses, some cost function tuning to make those things work. I don't think it's a robust technology yet because of local minima. Also, I would like to be able to optimize things of that complexity and much less compute. I think we shouldn't have to just naively simulate it. For the contact implicit, I would say is the same problem. It's the local minima in that problem are still bad. The mixed integer can be global if you're willing to hand it to a full branch and bound solver. But then in order to put it in that form, you tend to either embrace a combinatorial complexity, which then can be bad in the worst case, or you have made sacrifices in, like, you've linearized some of the nonlinear dynamics or even the nonlinear geometry in order to make those work. So yeah, people are still trying to make the mixed integer approaches faster, for instance, would be the number one thing. And then I think even if we were happy with the speed of them, we would have to address the gap in the linear approximations that we make. Because mixed integer nonlinear optimization is hard. That's it's very hard.
Maybe just because the examples you showed us were really simple, but it's hard for me to visualize what you mean by local minima.
I can definitely come up with complicated ones. I mean, the art would be to see if I can come up with only a little bit more complicated one. I mean, the classic local minima in trajectory optimization is like, I wanted to reach this way around the table, but I really, I'm currently thinking about reaching this way around an obstacle to get the mug, but I can't reach. And so I really had to reach, that was maybe the opposite of what I wanted or something, but like going left or right around the tree is sort of the canonical. Maybe you've been considering only going right around the tree, but at some point to accomplish the task, the wind is blowing or whatever, I really need to do something different. I need to go left around the tree. And that can happen in manipulation too. Like in tool use, right? If you're thinking about picking up the screwdriver and you really should have picked up the hammer, then it's very hard to like slowly stop picking up the screwdriver and start picking up the hammer, right? There's just sort of different valleys in the optimization landscape. And even for more narrow tasks, that happens. For loading the dishwasher, that happens for sure. I think the tree is probably as simple as I can, and you can imagine that being even for reaching, right? Reaching left or right around the edge of the sink in order to get into the sink can cause the same problems.
So is the idea just that it would look similar in the cost function, but in the end, the outcome is really different?
Yeah, I mean, you're not even the reason trajectory optimization can scale to these complicated things is because it's looking so narrowly, right? You can't, once the space gets very big, it's very hard to look everywhere in the solution space. So you're in a place where it would be worse to do locally, it would be worse to do anything different, right? Like I would have to run into the sink in order to get over to the place where the actual solution is.
Okay,
And so convincing yourself to, in the short term, do worse in order to ultimately find the right solution is you just, there's no local way to have that Oracle information.
I think maybe in the wall case, if you had a wall on the top instead of the bottom, then if your distribution doesn't cover any of the trajectories that collide with the wall, and you're trying to minimize the final position, it's a bit difficult because the gradient is telling you to go down in order to minimize if you don't touch the wall, if none of your things in the distribution touch the wall, and then suddenly changes. I mean, it's still local, right? Your distribution has to cover like this whole set of trajectories globally in order for it to work.
Yeah, good. Yeah. So right, the ball flying over the wall example has already got this, right? Because it would want to like slow down. Like in order to get the ball this way, locally, you would have to decrease x dot 0. But actually what you need to do is move down, hit the wall, and increase x dot 0, for instance, right? Isn't that what you're saying, Terry? No?
I think so. I did a horrible job of explaining, but
Yeah, I think that's exactly right.
So are you saying that in order to hit a position that's maybe behind your initial position, you could either throw it backward or throw it really hard against the wall such that it goes behind you?
But let's say you can't actually throw it backwards, right? That's because that if that was a solution, then maybe finding a solution would be good. But let's say I can't actually throw it backwards, but locally it's just telling me I should throw it less because then my ball at time 5 will be closer to this goal, right? And all the local gradient information is just going to bring you to 0 and then get stuck. When really what you needed to do was slam it against the wall and go this other way.
Okay, that makes sense.
can I maybe ask a small like implementation question? It's kind of dumb, but so like when I take an expected like gradient of the expected value of my reward, it's true that my like my distribution is kind of messed up in that example, right? So I need to keep track of like a bimodal distribution that some of which goes over the wall, some of which doesn't.
Taking that, so that's why people just do Monte Carlo approximations of that expected value, and then you can, if you're really taking a sum over lots of trajectories for that expected value, then the gradient is trivial. You just take the gradient of each of them independently and sum those two, right? But actually keeping track of the distributions and writing the expected value correctly is very hard.
I just couldn't work out the math in my head. It would help a lot.
We've tried. We've had cases where we used sums of squares to track level sets of the probability distribution through contact and watched sort of that multimodal, track that multimodal with a conservative outer bound. And I would love for that to go farther, but it's numerically hard to track those things. And still an outer approximation, or you choose your approximation, but there's like the occupations measures view of the world.